Welcome, Aaron. Welcome.
Hello, thank you.
Pijus, hello. Pijus, hello.
Hello.
Principal sir has also joined, so please start.
Okay. So, Namaskar and very good evening to all. It is a great honor and proud moment for us to organize the first memorial online lecture in the commemoration of our distinguished teacher, late Professor Haripada Pal, who served this Department of Physics, PK College, Contai during 1963 to 1995. This seminar is being organized by the Department of Physics, PK College, Contai, in association with the PK College, Contai Physics Alumni Consortium, with full technical and other support, necessary support from our Honorable Principal and the governing body of PK College, Contai, and also associated support from Dr. Kaushik Shankar Das of University of Maryland. In this occasion, we also like to express our regards to the family members of late Professor Pal in this occasion. In this memorial lecture, we have with us Dr. Kumar, the Honorable Principal of PK College, Contai, and he will as the President of this event. We have Dr. Kaushik Shankar Das, Department of Physics, University of Maryland, Eastern Shore, as the chief guest, and Dr. Aaron Persad, research scientist, Massachusetts Institute of Technology, United States, as today's distinguished speaker. I welcome all the dignitaries and all the participants in this Professor Haripada Pal first memorial online lecture. And first, I'd like to request our principal, sir, Dr. Amit Kumar De, to address the welcome note to the participants in this memorial lecture. Sir, please.
Thank you. Good evening to all. Actually, as the HOD Physics Department has told, that it's a memorial lecture in memory of Professor Haripada Pal, ex-teacher of the Department of Physics, UGPG. From last 4 or 5 years, we have started this type of lecture in the name of our renowned teacher, ex-teacher, who have served this institute for a long time. From that perspective, the Department of Physics, UGPG, they have started this online lecture. And on this hello, am I audible?
Yes, sir.
Hello?
Yes,
Yeah.
you are audible.
Okay. And in this proud moment, today we have Professor Kaushik from Maryland University, as well as Dr. Aaron Persad from MIT, which is both the university and both the institute is the main hub for the research and learning of physics. And from that perspective, we are very much lucky to have today's main person, Dr. Aaron Persad. As you know, Professor Haripada Pal, he was a very much famous teacher and a renowned teacher, and he had served his service life only for the development of physics, as well as the student of belonging to the Department of Physics. And from that perspective, today we have two great person, and I think their deliberation will add certain extra knowledge, so that in memory of Professor Haripada Pal, we can boost our beloved student. Yes, Pudipto, thank you. And today, we are very much honored to give tribute to Professor Haripada Pal after a long time, better late than never. And I think it's a great time also for us to have Dr. Aaron Persad and also Professor Kaushik, who will certainly add a new feather for the Department of Physics UGPG as well as for this age-old institution. We are going to complete about 96 years of journey in the field of education. And Dr. Aaron Persad will discuss on space, and perhaps it has both aspect theoretical and as well as the empirical. So the student and the teachers of our department will be able to get new light. Today, I also would like to thank to Prabhat Kumar College Physics Alumni Consortium, who have taken a lot of pain to organize this online memorial lecture. And they are also engaged effectively for the development of the department as well as for the development of our student. And every time they try to give certain impetus to our student of the Department of Physics. Actually, just after Corona, we have passed our long days by fighting with Corona pandemic. And as a result of that, we have learned how to converse, how to organize online meet, online conference, etc., etc. So from that perspective, Corona was our blessings. But I think the offline conversation will give a new light for the student and also for the teachers. So I hope after normalization of everything, that is after post-pandemic period, the department as well as Prabhat Kumar College Physics Alumni Consortium will organize offline meet so that the present student can get new idea by making conversation face to face. I will not waste time. On behalf of the college, I welcome all of you, especially Dr. Aaron Persad, who is from MIT, has given his kind consent to remain present here. Certainly, it's a proud privilege for us. And I also welcome all other person, teachers, the student, the alumni of the department, and if the teachers and the student from other institute, I welcome all of you and hope this online lecture will add new light, and it should remain a memorable day in our college history. Thank you. Thanks to Pijus, HOD. Over to Pijus Samanto.
Thank you, Sir, for this welcome address and introductory notes of this event. Now, I'll request today's chief guest, Dr. Kaushik Shankar Das, for his note. So, Dr. Das is presently an assistant professor of physics at the University of Maryland, Eastern Shore, and he's a very popular teacher, and he's very engaged in popularizing physics through various experiments in hands-on experiments so that students can enjoy the physics. So I'll request Dr. Das for his note. Over to Dr. Das.
Thank you, Dr. Samanta. Thank you, Dr. Panchadai, for inviting me to introduce Aaron. This is a great honor for me to introduce Aaron, who is not only an exceptionally good scientist, he has some other qualities also. So let me briefly tell you a little bit about Aaron Persad. Aaron and I are good friends. First of all, not only good friends, he is one of my best friends for last, how many years, Aaron? Maybe 15 years? Yeah, 14, 15 years. And we did research together when he was a PhD student at the University of Toronto, and I was a postdoctoral researcher there at that time. And we became friends from that time. I think it was 2005 or 6, from around that time. So it goes long way back. So Aaron does his research on theoretical statistical mechanics. He does very high level quantum statistical mechanics studies of evaporation and fluid and heat transfer. And his publications are really at the highest level journals. Recently, he has published one paper in an impact factor journal of 54, right? So that's the highest level of theoretical research. Now, he not only does theory, he verifies the theory with experiments also, hands-on experiments. And this is really important in Indian context. I'd come to that in a minute. And the story does not end there. He is not only a theoretician and an experimentalist, he is an entrepreneur also. So he tries to make those innovations into products. So he is the CEO and CTO of several companies, including some space food, very cutting edge companies that have started to operate now in $1 trillion industry in coming decades. So Aaron Persad is a theoretician, an experimentalist, and entrepreneur together. So this is what makes this talk very interesting. And what we can learn from Aaron is this real ecosystem, how the theory and experiment and entrepreneurship go hand in hand. And that is, to me, is the main difference between the science as we see in India and the science and technology as we see in the West. So I can say that because I have seen the academia and scientific environment both in India and in the West, inside out. And this is the main difference that comes to me, that when I see the Indian science context and Western science context, this is the main difference, that the Indian students are extremely good, extremely talented. They have exceptionally good understanding of mathematics and theory, but it's somehow the whole scientific community is more leaning towards theory only, right? So we are more interested in doing everything in our head or on pen and paper, rather than verifying it whether it can be observed or it can be verified in a tangible way as an experimental observation. So frankly speaking, India is very good. Indian scientific community is very good in theoretical research, but I'm sorry to say not so good in experimental observation. most likely the root of this problem lies way back in our thought process, in our thinking process. In our society, it is always encouraged that if you do everything in your head, if you do it theoretically, then these are the highest level of intellect or highest level of intellectuals, right? If you make your hands dirty, then that society thinks that this is not so good. This is like the person is probably not of the highest quality. This is a societal problem, and that's where all the problem begins. And what we have learned when we came out of India, that in the same lab where theory is done, experiments are done, numerical simulations are done, and from that research lab, you make products. Why is this important? Because unless and until you tie the research to your societal benefit, it is not going to succeed. This is the motto of the whole scientific movement in the West, that your research, yeah, obviously you try to learn something for learning's sake, but eventually that learning has to be tied with societal upliftment. There are a few small sage-like scientists will always be there who just focus on the theory, the how this universe came into being, from where we came, how we came, all these things. But let those highest level scientists or rishis be there and think about it. For most of the people, for rest of the scientific community, let us devote our talent and time in doing something for the society. If we cannot do that, then it's not worth it. This is what the philosophy of the West is, and it has to benefit the society economically also. The economic comes into play. What we do research here, next day it becomes a product, next day it goes to the market, it brings money back to the research community. And this is what the cycle is. If you break that cycle, if you break that ecosystem, if you don't care about what my research will do, I don't care about what whether it can be experimentally verified or not, then it's not a research for most of the people. This is what the common perception is, because without verification, a theory is just a hypothesis. This is very concrete statement I'm making. Without experimental observation, a theory is nothing but a hypothesis. Whether it is true or not, you don't know unless and until you do an experiment. So Dr. Aaron Persad, as I said, that he did a very high-level theory. He did a lot of experimental observation. He is the director of Bioastronautics at the International Institute of Astronautical Sciences, with the aim of preparing the next generation of scientists and engineers. And then he is the CTO of Mission Space Food. And he is the co-founder of that company. He is co-founder of multiple other companies. If the list goes on and on, it will take me 30 minutes to just read his bio. So I'll not take that much of time. I'll stop here and I will pass the mic to Dr. Aaron Persad for his important talk for the whole Indian science community. Thank you very much.
Thank you, Dr. Dash, for introducing today's distinguished speakers, and also enlighten our students participants to what the actual research should be. It should be a theory, an experiment which is performed in the laboratory with a focus towards the basic problems of the society, so that we can develop for the society, we can create industry, and then that benefit again comes to the research and development. So thank you again, Dr. Dash. Now I'll request Dr. Pradipta Panchadhyay to enlighten briefly on the life of our beloved teacher, late Professor Haripada Pal. And Dr. Panchadai is presently an associate professor of the Department of Physics, Prabhat Kumar College, Contai. So, Dr. Panchadai, please.
Yes, welcome. Thanks to the anchor. Regards to Honorable President of the event, welcome to the distinguished speaker, Dr. Aaron Persad, and the chief guest, Dr. Kaushik Das. We extend heartfelt thanks and gratitude for their gracious presence, especially to Dr. Kaushik Das for his constant support and enthusiasm towards the department. We feel privileged to have them on this online platform, which is dedicated to a great personality, Professor Haripada Pal. Professor Haripada Pal was the former head of the Department of Physics of our college. He was the architect of the honors department. It is very difficult to show courage to highlight all aspects of his colorful life in such a short span. Haripada Babu was born on 4th May 1935 in a very poor family in Baripur village under Potashpur police station of present-day Purba Midnapur district. He was the youngest child of his parents, 4 elder brothers and 1 elder sister. In 1942, the wave of the Quit India movement flooded all around. It was then that the wrath of nature hit this South Bengal, and the much heard super cyclone on Asin Sankranti in 1349 Bengali year. At that time, Haripada, a little boy, was studying from home, a student of 2nd class. Like many, the life of the boy, Haripada, was turned upside down by the storm. Because then came the tragic famine of 1350 to 51 Bengali year. Inevitably, the boy Haripada was the victim of extreme financial hardships. His father left him at a rich family in Moishadal. He had to work as a shepherd. Instead, he was provided with a meal. After some time, the owner felt that there was a fire in the boy and allowed him to go back to school. In 1944, Haripada was again admitted to the 2nd class. Haripada was the first in the class. He studied in the 3rd and 4th class grades from that house and repeatedly became the first. In 1947, his elder brothers came and forced him to get admitted to Bibishanpur school in 5th grade. The trend of being first continued, but again the rule was broken. Due to his ill health, he had to stay the 6th grade for a year more. In 1949, the headmaster of the school made him sit for the scholarship examination of class 6, and he became the first in the undivided Midnapur district in this examination. The headmaster of Bibishanpur school then admitted Haripada in class 7 in the school. He got the opportunity to study from 7th to 10th grade without any fee, without paying any fee. All the teachers of the school together used to help with books, leisures, tiffin, bear all the expenses of staying and eating in the hostel. In 1954, Haripada Pal passed the school final examination with the highest marks in the examination center, was admitted to the intermediate class in science in Tomluk College in July. The expenses of studying went on by earning money by teaching students. In 1956, after passing out with good marks in the science stream, the young Haripada got admission to Midnapur College with honors in physics. Acharya Banabihari Maiti, the then renowned professor of physics at Midnapur College, provided special assistance for admission. The source of income is the tuition, even while studying for honors. In 1958, after passing the physics honors examination with high marks, Haripada joined Hamilton School in Tamluk as a teacher in August. He suddenly got a chance to join a demonstrator in March 1959, but returned to Hamilton in May that year. In October of the same year, Haripada Babu took admission in the postgraduate stream of physics at the century-old Calcutta University. After studying in 61, in April, Haripada Babu started teaching at the Bakrabad school. After passing honors from Midnapur College, his guru, Banobihari Maiti, had taken a promise from him that when he wanted Guru Dakshina, he would have to give it. On January 1962, at the request of Banobihari Babu, Haripada Pal was appointed to Midnapur College as a professor. In 1962, the results of the University of Calcutta's master examination were published. Results were published. Haripada Babu took the sixth position. In spite of all these odds, in August 1962, he joined Maulana Azad College in Calcutta as a professor. In the meantime, Acharya Banobihari Maiti became the principal of Prabhat Kumar College, Contai. Responding to Guru's affectionate call, he joined Prabhat Kumar College, Contai on 1963 as a teacher to fulfill his promise. In the same year, with the outstanding work of Acharya Maiti sir, this college had just opened the honors course in physics, and Guru Banobihari Maiti's main choice for this formation of this department, this honors course, was his favorite student, Haripada. Haripada, who started decorating the honors department with childlike affection. He devised a plan to create a standard UG laboratory facility. The physics department of the college continued to develop a reputation in both theoretical and experimental studies. In this regard, the contribution of his distinguished colleagues is also worth mentioning. He could go deep into the content easily in short speeches through a simple and lively teaching style. It was only through his teaching style that he became proverbial. Under his unparalleled leadership, with the help of able colleagues and working teachers, an ideal atmosphere of education was created. The Department of Physics reached an extraordinary height. The key to Haripada Babu in the way to progress was the mantra of unity. On May 31st, 1995, he retired from his teaching position of the college. In his retirement life, he was almost obsessed with the culture of philosophy. He tried to give philosophical explanation of scientific thoughts through his understanding. Acharya Pal was the professor of rare quality. His keen accountability and frank approach to truthfulness, even unfavorable, is a special aspect of his character, and the strict morality is another notable feature. He also had to be the target of attack for these characteristic qualities. Throughout his life, Haripada Babu lived a very simple life. The name of simple lifestyle and honesty was Haripada Pal. Throughout his life, he wanted to instill the same ideals among his 3 sons and 1 daughter. And remarkably, he didn't fail. As an unparalleled popular ideal teacher rooted in the excellence of his life, thoughts, and teaching, he has secured a permanent place in the hearts of pupils. So, giving this introduction, I am ending here. So, over to the anchor, Dr. Samanto, please.
Thank you, Dr. Panchadai, for enlightening us with the life and work of Dr. Haripada Pal, who started this department for a long time and make a development. So, although Dr. Das has already introduced Dr. Persad from his various aspects of research and achievements, but I like to briefly summarize its academic and professional affiliations in various institutes and achievements. So Dr. Persad completed his PhD in 2006 at the University of Toronto in the biomedical stream of engineering science. His undergraduate thesis with the bone interface group at the Institute of Biomaterials and Biomedical Engineering investigated the effects of subtle launch vibrations on the proliferation, viability, and conformation of the stem cells derived from human umbilical cords. He completed his PhD in statistical thermodynamics and quantum mechanics in 2014 at the University of Toronto with Charles Wall Group. There he investigated heat transport mechanisms for both ground and space applications, accumulating in 2 launches of his payloads to the International Space Station. He pursued a postdoc in micro and nanofluidics phase change kinetics with David Stanton Group at the University of Toronto. Dr. Persad is currently a research scientist in mechanical engineering at the Massachusetts Institute of Technology with the Rohit Karnik Group, where he is developing nanotechnologies for purification, dialysis, treatment, and fusion reactors. He is the director of Bioastronautics for the International Institute for Astronautical Science, board members of the Association of Spaceflight Professionals, co-founder of Astris, a company innovating space food systems, and recent winners of NASA's Deep Space Food Challenges Phase 1 with his team mission, Space Food. So these are only a few that we have mentioned over here. So there are lots of
answer. It's to find the reason why we exist, why we're here. And so if we think about space sciences, I like to divide it into things that are alive and things that are not alive. So things that are alive, for example, you've probably heard the term biology, which really means biologos, the reason why living things are the way they are. Physiology, again, physiologos, psychology, physiology, and so on. And in the physical world, you hear terms like rheology, like the reason why fluids flow the way they do, or cosmology, the reason for the stars. So I have here some photos and examples that at a high level provide some diversity of the studies that are done in space sciences. I'm going to see if I can bring up my laser pointer. Let's see, or I guess my arrow. So the first image I have are water bears. These are tiny microscopic organisms that have been brought into outer space. Actually, they've been put outside of the International Space Station and exposed to the very harsh temperature swings and radiation of space and low Earth orbit. And they have been found to survive in those environments. And so there's a lot of interest in the space science, life science world to understand how living things can survive in outer space, and that leads into the search for life, if there's life elsewhere. The second set of images that are labeled A to I, these are showing how plants grow in space. So A, B, C sort of shows the sequence of what the roots look like if they grow on Earth, and D, E, F is showing that the roots are moving downwards towards Earth's gravity. But in G, H, and I, it's showing that the same effect can be achieved using other stimuli like light, and the roots that are formed become a lot more chaotic when grown in space versus when grown on the ground. And so this is leading towards how can we grow plants, vegetables, fruits, so on in space, and what insights does that tell us about living organisms surviving outside of Earth? In this almost center image on the left, I have here 2 astronauts that have a neural cap on one, and they're studying the brain waves and basically human psychology and physiology and how the human body reacts to space. A lot of the astronauts that are on station orbiting the Earth, whether it be in the past from the Mercury, Gemini, or the Apollo missions, or the more current Skylab, Mir, and International Space Station, humans are being treated as test subjects so we can understand how the human body adapts, evolves, quotation marks, and whether or not we can survive on a different planet or in outer space for extended periods of time. I think the record is just just slightly more than a year in space. I think that was Scott Kelly, continuous time. But can humans survive 3 years continuous time in space or 5 years? These are big questions that want to be answered in space sciences. And then moving to physical sciences, I have here an image of a candle. You've probably seen a birthday candle, and you know what a flame looks like, the shape and the color. But if you take that same candle and burn it in a microgravity or weightless environment, the flame looks very different. You have a duller color. It's almost like a spherical cap. The flame is blue. And there's a whole reason for why the flame behaves the way it does, but it just drives home how different physical systems can behave in space versus on Earth. Going downwards at the bottom right, it shows the potential application of how we can exploit the environment of space to help improve life on Earth. So in this bottom image with the crystals, on the right side, it shows the crystals that are grown on Earth. So these crystals can be protein crystals that are used for X-ray diffraction to understand protein structure to help with drug development, or they can be semiconductor crystals that are used to create electronics that are in your phone or in your computer. And on Earth, the challenge is how do you grow a crystal that's uniform and doesn't have a lot of defects? If you take the same solution and grow it in the microgravity or space environment, you get much larger crystals. So what this means is you get higher resolution of protein structure, or larger wafers of semiconductors to make electronics, higher quality electronics. And so there's a direct benefit back to Earth for studying space sciences. At the bottom center image, it's showing how liquids can flow by capillary action. So you have a liquid here moving against, if you will, what you would expect a liquid to do. It's moving upward, and it's entirely making use of surface tension dominated forces, which can be exploited in space. And so there's new designs for containers and fuel pumps and so on that can exist in space. And finally, at the bottom left, I have a photo of water in a jar. On Earth, the leftmost image, the water is at the bottom. You have this slightly curved interface. But if you take the same system and put it in a microgravity or weightless environment, the water breaks off into these multiple interfaces and bridges, and you have more spherical type interfaces. So this is a high-level overview, not at all exhaustive, of some examples of space science work that's done. Now, for the second part, I want to get into theory and the scientific method, and I'm going to talk about thermodynamics. And so I want to just set the stage at a high level. So thermodynamics tells us what will be the equilibrium state of a system. So given initial conditions, if I allow the system to evolve to its final state, thermodynamics tells us what that final equilibrium state will be. So it's the study of how energy changes forms between heat and work. And thermodynamics, very importantly, is based on postulates. Postulates are statements that are taken to be true without any proof of those statements. But the statements allow us to form predictions, and those predictions can be tested in the lab. And so if the predictions are tested and validated, it provides support for the postulate that we make. And so one of the basic postulates of thermodynamics is that you have a system, it has an internal energy U, and that internal energy is a function of the entropy, S, the volume, N, V, and N, the number of molecules or particles that are in that system. And so in thermodynamics, we often will look at steady state conditions, homogeneous versus non-homogeneous systems, and dynamic versus static systems. Now, I love studying thermodynamics And one of the reasons why I studied thermodynamics for a PhD was because of what Albert Einstein said here. He says that it's the only physical theory of universal content, which means that it's applicable in life, in robotics, in the atmosphere, universal content concerning which I am convinced that within the framework of its applicability, of its basic concepts, it will never be overthrown. So to paraphrase, Albert Einstein is saying that thermodynamics, you can apply it everywhere, and it's unlikely to change with time. And this is in contrast to if you study medicine, for example, where you make a new discovery and now almost everything that you've learned about a particular drug or a particular way of treating people now has to be updated and changed to reflect the new discoveries. Or if you study archaeology, every time the shovel goes in the ground and you discover a new civilization or a new weapon or spear or pottery, you have to rewrite human history. But in thermodynamics, Albert Einstein is saying that this is a field that's likely to not change. So I took great comfort in that, and I pursued thermodynamics for my research. Now, there is a field called non-equilibrium thermodynamics, and non-equilibrium thermodynamics tells us how the system reaches equilibrium. So thermodynamics tells us what is the equilibrium state. Non-equilibrium thermodynamics tells us how the system reaches that equilibrium state. And so I've listed here some processes that you're probably familiar with: evaporation, condensation, freezing, adsorption, desorption, chemical reactions, changing fields. All of these are examples of systems of non-equilibrium. And what I'll be talking about for the majority of this presentation is evaporation processes. So to put the context of why evaporation is important, we're probably all familiar with climate change. And it's no surprise that water grand challenges drive the need for fundamental research into evaporation. To put it simply, as humans, we need water to survive. And our planet is showing signs that water is not behaving constantly. It's a renewable resource, but things are changing with climate, and we need to find a way to understand why those changes are happening and how to provide water security. So I have here a map showing water scarcity across the world. And if you were to plot this map over time, you would basically see that there is a growing amount of water scarcity in the world. Lakes and reservoirs are drying up, ground is losing moisture, and what that means is that the water is moving from lakes and reservoirs to somewhere else. And what's happening is water is being displaced on a worldwide scale to other places. And so some people have droughts, but other people have floods and severe snowstorms. And there's other factors that are playing a role, like anthropogenic, which means human cause factors as well. But hopefully I convinced you that it's important for us to understand how water moves from one location to another and what are the driving mechanisms of that, and how can we use that knowledge to provide security to the world. For my generation, probably this will resonate more. It's how do we use cooling technologies using evaporation to drive more powerful electronics. So we want cell phones, for example, that are more powerful but smaller and lighter. And what that means is we have to pack more transistors into a smaller form factor. And those transistors are going to generate a lot of heat as they operate, and so we need to cool them. And so evaporation is one way to provide a nice, compact cooling system. But how can we push the technology even further? And as Dr. Das talked about, how can we then spin that off into new technologies for consumers, for satellites, for maybe defense and military and other applications. And then some other applications here of studying evaporation is it helps us to understand what happens in other planets, which in turn will help us understand how they formed and how the universe and the solar system formed. But on the other side, there are some more creative ways of how can we use evaporation to develop new ways of humans to interact, new fabrics. For example, here at the top left from the MIT Media Labs, where I'm located, they're looking at creating new art forms, but also new technologies to tell you when your tea is hot enough or ready, or to turn on a lamp using evaporation. Like, these are wild ideas. And evaporation also plays a big role in pharmaceuticals, and that's a huge trillion-dollar industry. And so if we can make the process more efficient, we can reduce costs, and that's going to benefit people who need to use these types of drugs. So the scientific method is one of the main tools that scientists use to understand the world around them. And in this flowchart, you basically ask a question, you do some background research, and you form a hypothesis. It's like, I think things behave this way because, and here's my hypothesis. And then you design an experiment to test out that hypothesis. You verify your experiment works. If it doesn't work, you debug it and try again. And if it does work, you collect your data, you draw your conclusions, and you see, does your data support your hypothesis or not? If it supports your hypothesis, that's great. You communicate those results to the community. Or if it doesn't support the hypothesis, you can also communicate those results to the community, but you also have a new starting point, new data to construct a new hypothesis. So the scientific method works if the scientists remain objective. If your goal is to develop a theory and prove that theory is correct and push it regardless of what the data says, now you're no longer objective, you're being subjective. In order to be objective, you need to have empirical data, not what you wish to happen or your interpretation. And so you need to have empirical data that when different people look at the data, they see the same data. The explanation of what that data means might vary between scientists, but the data itself is empirical and hopefully objective. And then what do you do if the theory should be correct, but you find that the experiments don't agree? This is the big question that every scientist faces. You think your theory should be correct, but it doesn't agree with experiments. What do you do? And oftentimes you can argue that maybe there's something wrong with the experiment, and so I'll do some more experiments. And if it still doesn't agree, you'll say, okay, maybe something was still wrong with the experiments. Or you have to be ready to say, hey, this theory is wrong, and we need a new theory. That is the power of the scientific method if we remain objective with it. So now I'm going to apply that to talk about a very specific example of classical kinetic theory versus statistical rate theory. So this is the part 3 of the talk. So classical kinetic theory is basically the main theory that has been used for the past 130 years to describe evaporation, this non-equilibrium process of phase change. And the theory was formulated essentially by these 4 people here, Maxwell, Boltzmann, Hertz, and Knudsen. So in the theory, it assumes that gases are in equilibrium, and the gas molecules have a velocity distribution that's called the Maxwell-Boltzmann distribution. And I'll talk a bit about what that means. And then if you have a liquid vapor system in equilibrium, then the liquid molecules must also have the same distribution as the gas molecules. If they had a different distribution, you would have a non-equilibrium system. And so those 2 statements, there's nothing wrong with them. Gases are in equilibrium, they have a Maxwell-Boltzmann distribution. If the liquid is also in equilibrium with the gas, it must have the same distribution. Nothing wrong there. Now, what happens if a liquid is evaporating? Well, clearly the gases in the liquid are not in equilibrium with each other. But Hertz and Knudsen assumed that the Maxwell distribution would still be valid for evaporation. So this is an assumption that they made. So we're going to look at some high-level models of the classical kinetic theory model of gases. So you have gas molecules in a box, and those gas molecules are constantly moving around and hitting each other and the walls of the box. So you can think of it as tennis players hitting a ball back and forth. if you're to average the movement of the gas molecules, or in this case, if you're to average the movement of tennis balls as they're being hit back and forth, you'll find that there's a velocity distribution, that some of these tennis balls will have velocity in a slow range, in a very high range, and also most of them will be in this average velocity range. That distribution, going back to gas molecules, changes with temperature and so on. But that's essentially the heart of the Maxwell-Boltzmann distribution. And so if you have a system where gas molecules are in contact with liquid molecules, and there's an interface where free exchange of the molecules can take place, well, if these gas molecules are moving around with the Maxwell-Boltzmann distribution, some of them are going to collide with across the interface and condense, essentially. But at the same time, the molecules in the liquid are also moving around, colliding with the containers, perhaps at a different velocities, but some of them are going to collide with the interface and escape into the gas phase. And so this rate at which molecules collide with the interface, this is called the uniform transition flux. So I call it here KE, and E, the subscript E is indicating equilibrium. So at equilibrium, these two rates have to be the same. And it's a function of the pressure of the system, the temperature, and constants related to the mass of the molecules and the Boltzmann constant. So in equilibrium, great. You have those two rates are the same, and the net evaporation rate is just the difference between these two rates. If you're the same, that's going to be 0. And if you're curious about the units, it's kilograms per meter squared per second. Now, if you have a system that's evaporating, necessarily what that means is that the unidirectional condensation rate flux has to be less than the unidirectional evaporation flux, okay? And so in equilibrium, the two rates give 0, but in evaporation, assuming what Hertz and Knudsen assumed, that the Maxwell distribution was still valid in this non-equilibrium case, well, now the unidirectional condensation flux will depend on the pressure of the liquid, the temperature of the liquid, and the unidirectional evaporation flux is going to depend on the temperature of the vapor and the pressure of the vapor and the temperature of the vapor, and the net evaporation rate is going to be the difference between these two rates, and that's going to depend on the pressures and the temperatures. Okay, so very, very simple concept here. Now, what was found, that's the theory, when experiments were conducted, what was found was that the evaporation rates were much smaller than what was predicted, much smaller, anywhere from 10 to the minus 1, 10 to the minus 4. So almost 4 is magnitude smaller. And so going back to this scientific method, I'll just very quickly go back to the slide. What should you do if the theory is not correct? If it doesn't agree with the experiments? Well, what the community has done is they really wanted to keep the theory, and so they added more terms to the theory. So they added what's called the evaporation coefficient and the condensation coefficient. The evaporation coefficient basically means if a molecule evaporates, maybe it'll hit other molecules in the vapor and recondense. And so not all molecules that cross the interface stay in the vapor phase. Some will come back to the liquid phase. So what fraction of molecules stay in the vapor phase? That's the condensation coefficient, evaporation coefficient. And a similar idea for condensation. Some of the molecules might be reflected when they hit the interface, but some will condense. And so the fraction of molecules that condense versus the total number of molecules that cross the interface is called the condensation coefficient. And so these terms have been added to this equation. And for those of you who are sharp, you will notice something particular about this equation already, okay? Now, here it is. We have one equation for the evaporation flux, which depends on temperature, pressures, which I can measure, but I also have the evaporation coefficient, the condensation coefficient. One equation, two unknowns. Is this equation solvable? And hopefully all of you will say no. it's not solvable because there are two unknowns, one equation, it's closed. And so at this point, what should be done is maybe re-examine the theory. I'm very sharp here and I say maybe abandon the theory, or you have to make simplifying assumptions. And so you have to assume that maybe the coefficients are equal, and that'll reduce this to one equation, one unknown. And another assumption that's done by the community is to assume that these two temperatures across the interface are the same. Okay, so these are assumptions that are made. If you make those assumptions and you do the experiments, for one experimental condition, you get a tremendous scatter of this value of sigma. So you can see here, if I pick one condition, just if you look at one vertical line, there are multiple data points that cross that vertical line. And so you have a theory here that people have been holding on to for 130 years, and it's leading to just ridiculous scatter with experiments. It's just not agreeing. And what the community always concludes is something must be wrong with the experiments. Maybe the experiment wasn't done right, wasn't measured accurately, there was contamination. They held on to their theory and they didn't want to believe what the experiments were saying. So that motivated the doctoral work to study statistical rate theory. And this is a new theory of evaporation that isn't based on classical kinetic theory. It's based on quantum mechanical theory and state transition probabilities. So at a high level, this is how the theory works. You have two simple material systems. You have a liquid and a vapor. And let's assume that a molecule is in the liquid phase. SRT, statistical rate theory, asked the question, what is the probability that a molecule will transition from the liquid to the vapor phase within a certain time interval? That's how this question is formulated. Now, in the liquid phase, you have different quantum states. So you can never know the energy precisely and time precisely. There's always a trade-off between the two. And so within the uncertainty of the system, there's a number of degenerate quantum states that the system can have. And these exist in the liquid and in the vapor. And so the question in quantum mechanics becomes, what is the likelihood that you are in one of these quantum states in the liquid and that you will transition to any one of these quantum states in the vapor within a time interval delta t? So to put that mathematically, it's shown here. So the probability that you're in one of these quantum states, it's just 1 over the number of quantum states that you have. The probability that you'll transition to any one of these quantum states is just multiplied by the number of quantum states you have in the vapor. And then you have to have a term that says the number of these transitions that take place within this time interval delta t. So that's this k term. And then using definitions of Boltzmann definition of entropy and so on, you can formulate. So this becomes this ln number of quantum states, and then the ln goes into the exponential when you calculate the differences back and forth. And so at a high level, you get an equation that looks like this. It's the evaporation rate is a function of the number of transitions that happen and the entropy associated with transitions in the forward direction and in the backward direction. Okay, so just at a high level, that's the description. And so if we look at this equation, it has a similar form as the classical kinetic theory equation. It's the difference between a unidirectional condensation flux and evaporation flux. But the difference is that the evaporation rate isn't just a function of the mass of the molecules, the pressure and temperature. It's also a function of the properties of that molecule. So if we look at water, water has different vibrational modes, bending, stretching, asymmetric stretch. And so the quantum mechanical theory takes all of these motions into account. It also takes into account the fluid properties of water, saturation pressure, its specific volume, or 1 over density, and surface tension. And it takes into account the shape of the interface. And so that's the theory. How do we test if this new theory is accurate? So what we did was we built an experimental setup, and because we knew we were challenging 130 years of research, we needed to have a very precise, highly reliable experimental setup. And so the setup is shown here, and at a very fast description, we control the atmosphere inside the evaporation chamber. So basically, we remove air, and we just have a single component system. If it's water, it's just pure water into its own vapor. There's no air. In the system, we have a microthermocouple. You can barely see it here. It's 12 microns in diameter, 24 microns in diameter. And we use it to measure the temperature profiles in the liquid phase, in the vapor phase, the liquid phase, and along the entire surface of the droplet. And we have some systems in place to help ensure the purity of the system and to help us measure the evaporation rate. Essentially, we form a droplet of water. We reduce the pressure. As the water evaporates, the height will decrease, and then we inject water from a syringe pump to keep the height steady. And so we can read the evaporation rate by reading the pumping rate, and we have the pressures measured, and we have the temperatures all throughout, and we monitor the positioning of the thermocouple and the interface with a capthometer. It's like a telescope. And so we have a steady state system, high purity, with very high precision temperature measurements. And this is what we found. So if you look at the interface of the water droplet here, we're on the central line. And as I move my thermocouple closer and closer to the interface, I see that the temperature is getting colder and colder as I move towards the interface. And then if I take the thermocouple and dip it into the liquid and move away from the interface, I see that the temperature gets warmer and warmer as I move away from the interface. And this is the most surprising result that we found. We found that there is a temperature jump, a discontinuity across the interface. So as the thermocouple goes from the vapor side right into the liquid side, there's a temperature jump, and it's quite significant. Here, it's about 2 degrees. We've done experiments where it's up to 15 degrees jump. This is amazing. This means that your cup of water, there is a temperature jump. This means that the ocean being heated by the sun, there's a temperature jump. This means that if you're studying atmospheres elsewhere, like on Mars, and there's water that's melting and so on, there's a temperature jump. And this is in direct conflict with classical kinetic theory. If you remember, they assumed the temperatures were the same. And so this was a fantastic discovery, which led to multiple publications. And as Dr. Das mentioned, we published in chemical reviews. And I looked up the impact factor while the talk was going on. It was 60, impact factor of 60 chemical reviews. So we can do these experiments at different evaporation conditions. And going back to my theory, if I measure all of these terms, the pressures, the individual temperatures, I can measure also the evaporation rate. I can back calculate some of these properties. And so what we did was we ran a whole series of experiments and calculated the saturation pressure of water or of ethanol at different temperatures. We used water, we used ethanol, different molecules to test out the theory. So I'll show the results here for ethanol. So on the y-axis, we have the saturation pressure that we calculate from our statistical rate theory. On the x-axis, we have temperature in Kelvin. And the purple circles are the data that we got from our experiments. And the black dots are data that's reported by DIPPR or NIST. These are highly credible databases that everyone uses in industry. And the first thing you'll notice is that if we fit a curve through our own data, the curve matches this data point from that database, but it doesn't match this data point from the database. The error is about 10%. And we spent a year making sure that the experiments were correct, because we thought, oh, this database is so of high reputation, maybe our experiments are wrong because we're not matching it. But eventually what we found is that our data was extremely accurate, and therefore the data in the database must be wrong. And so to show that our data is very accurate, we took the slope of this curve and we can calculate the latent heat. And then we took the slope and compared it to data from this database, DIPPR, and it went right through the data. And then if you take the second derivative derivative of the slope, you get the specific heat. And so we took the second derivative of the slope, we get this line shown here, and then we went through the literature and collected all the data we could find of people who reported the specific heat of ethanol. And our data went right through it. And this is our experiment range. We just collected data in this temperature range, you can see here, just very small temperature range. But even if we extrapolate our curve almost 3 times past our experiment range, it still goes through all that data. And so this provided extremely strong support that, one, we can predict thermodynamic properties using non-equilibrium experiments, but more importantly, that this statistical rate theory was correct. Okay, so I'm going to move on now to talking about weightlessness, and I'm going to come back to talking about liquids and thermodynamics and so on. So when I talk about microgravity or weightlessness, what do I mean by that? I'm going to go through these very quickly, these slides. So I apologize if it's too fast, but just so I can get on to the more interesting things. So you probably hear astronauts say, hey, things float in space because there's no gravity up there. That's not true. But gravity is also spoken about in terms of a force, an acceleration. Sometimes it's talked about as a constant. So is it any of those? Well, the way that we answer this question is we build upon the research that was done by Galileo, Newton, Cavendish, and they basically played a role in forming the laws of motion, Newtonian laws of motion. Galileo played a role in measuring the mass of the Earth and the size of the Earth, the radius of the Earth. And Cavendish played a role in measuring the universal gravitational constant. So if you equate, M1 is referring to just any object you have on Earth. So if you equate these two force equations, the M1s cancel, and we have all these properties, the mass of the Earth, the size of the Earth. You can then calculate G, and for most cases, G comes out to be 9.81 meters per second squared. But I have a graph here to show that in reality, G varies significantly depending on where you are. And it's based on the density of the Earth, the elevation of the Earth, and so on. But what you also notice is that as you move away from the surface of the Earth, the acceleration due to Earth's gravity, so G is definitely an acceleration, tapers off, but doesn't quite drop to 0 as soon as you leave Earth. Actually, one of the only places you can get 0 G is if you were in the center of the Earth. So there's definitely gravity in space, and in fact, the International Space Station that orbits at 400 kilometers above the Earth experiences about 90% of G. So very strong gravitational field is pulling the International Space Station and having it orbit the Earth. So then why is Julie Payette, she's a veteran Canadian astronaut, why is she floating in space if the gravitational field is so strong? And to answer that, we can look at a free body diagram. So here I have Julie Payette. I have this image of a girl on the ground. She's clearly not floating. What's the difference between these two? Well, for the case of the girl on the ground, her mass in the gravitational field is exerting a force Fg, and the table or the ground is exerting a force, normal force, reactive force, in the opposite direction of equal magnitudes. And so the net force is 0 and she doesn't move. In the case of Julie Payette, there is no table, there is no floor. So Julie Payette is experiencing a force of Fg, but so is the space station. And so everything is falling together. And so from our reference viewpoint, it looks like she's just stationary, but in actuality, she's orbiting the Earth with the station. And so what this means is that you can also experience weightlessness on Earth just by jumping. The moment your feet leave the air, you are experiencing exactly the same environment that astronauts experience on the space station. So that's weightlessness. And now I want to talk about how liquids behave in weightlessness. So why do we care? Well, we need to design rockets, space stations, satellites, spacesuits. All of these require that a liquid be stored in a container, and they're going to be exposed to the weightless or near weightless environment. In fact, in 2013 in July, Luca Parmitano, he's an Italian astronaut with ESA. His spacesuit, one of the filters failed between the air and the water pumps, and it started to pump water into his helmet. And how water behaved in that closed environment of the helmet became extremely important because he almost drowned. And so there is a huge question right now of studying how liquids behave in sealed containers in a weightless environment. So I have here some examples of water in a cylindrical glass container, pure water vapor, and it's borosilicate glass, so very pure system. There's roughly about the same amount of water in both of these containers, but you'll notice that one container is taller, probably 33% taller than the other one. And so one of the questions of thermodynamics is what will be the equilibrium configuration of water in these containers if I bring it into the weightless environment? And the question is, what is the stable configuration? So if I take that container and shake it on Earth, I know the water is always going to be at the bottom, the vapor phase at the top. But if I take this container into space and I shake it and let it settle again, what will be the equilibrium configuration? So I have here some examples. This is not exhaustive, but just some examples of how the liquid could behave. It could form a single interface, double interface, a bridge, a bubble, a droplet, a sessile droplet, or a sessile bubble. In the chat, I'm going to ask you, let me know what you think. Is it going to be A, B, C, D, E, F, or G? Take like 10 seconds and tell me how you think this container, this larger one, will behave if I were to bring it into the space station and let it free float. Okay, 10 seconds.
Yes.
Okay, great. So hopefully you put your answers into the chat. The way that we tested this was we ran an experiment. So with Charles Ward, Dr. Das is also very familiar with this experiment. We took cylinders, we had them in different orientation, different sizes, and they were all designed to form a certain interface configuration. This payload was split into what's called the Getaway Express Special. It's basically a garbage can size container that isn't operated by the astronauts. It just sits in the high bay of the space shuttle. You can see there are two astronauts out here working. This is Winston Scott, and I got to meet him in February and talk about this experiment because he was right there with it. And we just leave it out there, the space shuttle, in the weightless environment and see how the liquid behaves. And so this is what we found. We found that the system went into the double interface configuration. So for those of you who said it would be B, congratulations. But what we saw was that the interface wasn't symmetrical. It was asymmetrical. There was a different shape at the bottom and at the top. What could cause that? What could cause it? Our theory says they're going to be equal and symmetrical and double interface. The experiments show that it's not. So what we found is that as the space shuttle orbits the Earth, there's a certain velocity that the shuttle has relative to the orientation of the payload. And it's in low Earth orbit, so there are micrometeorites that hit the shuttle and slow it down. And so what we found, or what we think happened, is that there's an acceleration acting on the fluid. And so we calculated what acceleration would be needed to form this interface shape, this hysteresis. And we were able to compare what we measured, which was roughly 10 to the minus 4 Gs, with the accelerometer system that was on the space shuttle. The space shuttle has three $13,000 accelerometers as part of the SAM system. And this particular mission had another experiment that was specifically testing different accelerometers. And so we had very good accelerometer data to test against our theory. And what we found was a match, perfect match, with what the accelerometer said and what our fluid cells said. The advantage of the fluid cell is that they don't have to be calibrated. You just take a picture, and if you know the temperature, that's it. With these accelerometers, they drift over time and they constantly have to be recalibrated. So this was an amazing discovery. Now, what you'll notice is the image is not very clear. It's kind of fuzzy, a lot of reflections. And so what we did was we got the cylinders back from the space shuttle, and we rebuilt one of the cylinders for the International Space Station. The key here is the cylinders are curved, and in order for us to see the interface clearly, we need to have an index of refraction matching liquid that would bend light the same way that glass bends light. And we put that in a rectangular prism. So now when you look at the cylinder, you can clearly see the interface free of any diffractions and refractions of the cylinder. So this was put together in Ward's lab. This is Bjarne Tryggvason, who's a Canadian astronaut retired. We built the payload ourselves. We tested it out. This is what the payload looked like. And we launched it on SpaceX Dragon 7. This was in 2000, I think it was 2013, if I remember, or 14. Unfortunately, 2 minutes into the launch, the rocket blew up. This is the only SpaceX Dragon rocket that blew up. It happened to be when our payload was on it. What happened was the supplier for a beam that holds up the oxygen tank, they cut some corners and the beam failed during the load of the launch. The oxygen tank crashed into the rocket and blew it up. But we rebuilt the payload and flew it on Dragon 9 in 2000, I think it was 16 or 15. And that one made it to the International Space Station. So our payload is here, the Dragon 9 capsule. This is the Canada arm catching the payload, and it was brought into the space station. I'm still waiting for the data from it, so I don't have that to share. But in the meantime, we've continued with experiments in parabolic aircraft. Let me turn this down. So parabolic aircraft, it's a regular aircraft that you fly on Earth, but you fly it in a parabola sequence. And what this does is it gives you about 20 seconds of this weightless environment. Remember, the aircraft and you and everything in the aircraft is free falling. So from your perspective, it looks like things are floating. And so I'll play that again as I'm talking. So the way that the aircraft does the maneuver is it goes about 24,000 feet above ground. It pulls up and rises about 10,000 feet. During the climb, you're experiencing 2 Gs. Then it pushes over and you basically free fall for 10,000 feet, which equates to about 23 seconds. And then you recover the aircraft before it crashes. You pull out at 24,000 feet at about 2 Gs. Dr. Das is well familiar with this. He and his team at UMES developed a payload to study how objects rotate in a microgravity environment. So I put this slide here to show some of the great work that has come out of his lab in terms of payloads, theory, and putting together some very professional looking payloads that we flew in the aircraft. So back to this question of how liquids behave in microgravity. So here is a picture of what the interface looks like in this new acrylic box that we designed. And for the parabolic aircraft, I had a very large cylinder and 2 smaller cylinders. And this was to study how quickly the liquids would transition to equilibrium states. This is the aircraft, the Falcon 20. It's a business jet. And I also developed a brain teaser payload, which I'll talk about a bit later. So these are the payloads mounted to the aircraft. And the payloads were designed so that they would be bolted to the aircraft and experience all the vibrations and accelerations of the aircraft. And then we can also release the payloads and free float them. Each payload had a camera and an accelerometer system. So this is showing, hopefully the video comes across, but this is showing what the larger cell looks like when it's bolted down to the aircraft and the aircraft goes into the microgravity environment. So you can see it wants to take on the double interface shape. It wants to do it. but 20 seconds just isn't enough time for it to happen. And you can see that there is a hysteresis between the bottom and top interface of the payload. What was interesting, I don't know if you noticed, but the smaller cylinders did not react at all to that. This is the same payload, free floating. If you can see the horizon here, you can see the aircraft is climbing at roughly 45 degrees to the horizon. It's in 2 Gs, so in 2 Gs, the interface is going to be a little flatter than you would see on the ground. And then as we enter microgravity, look at what happens to the interface. Much more symmetrical. You know, things are moving, people are handling it, but you can see that the interface is a lot more symmetrical. Okay, so I took screenshots. This is what the interface looks like on the left in the 1.8 G climb. The center photo is showing what the interface looks like when it's mounted to the aircraft. And the photo on the right shows what the interface looks like when it's free floating. We calculated the Gs based on the interface contact angles. And we found that this is 10 to the minus 6 Gs, really microgravity. And this is 10 to the minus 7 Gs. So the key takeaway here is many scientists on the space station assume that they are operating at a 10 to the minus 6 G level. They're assuming that that means zero gravity, 0 G. But you can clearly see the impact that 10 to the minus 6 Gs can have on a system as simple as liquid in a container. So what this means is there's a lot of work that needs to be done to develop new technologies to create an actual 10 to the minus 6, 10 to the minus 7 G environment. So here's the brain teaser I have for you. And I built this, this container. It's out of acrylic. And there are 2 chambers at the top and the bottom that are filled with water that's been dyed red with food coloring. The different chambers that connect the 2 chambers at the top and bottom are shown here. One is an hourglass shape, one is a diamond shape, and then I have a large rectangle, medium rectangle, and a very thin rectangle, almost like a capillary. So my question to you, this picture was taken on the ground. It's designed so that capillary forces dominate. And you can see here that all of this water is being held up by this interface. But what would happen if I were to bring this system into microgravity, let it free float? So I have these different channels. There's a reservoir at the top and bottom that connect all of them together. What do you think will be the equilibrium configuration in microgravity? While you're thinking about that, I'm going to talk about thermodynamics at the nanoscale. So all this work that we did studying how liquids behave in microgravity, surface tension forces dominate. Well, at the nanoscale, surface tension forces also dominate. And this is especially important practically in oil and gas industries, where instead of drilling to the ground and having oil gush out, which is conventional oil, oftentimes what has to be done now is drill into the ground and pull the oil out of the microfractures that are in the ground. And these microfractures often have features that are at the nanoscale, so it's called kerogen. And so what we did in Sinton's lab was we studied how liquids evaporate and phase change in these tiny microchannels. And we also developed technologies that allowed us to visualize the liquid and vapor phases in a microscope in small channels. You need to do some special work to be able to see the 2 phases, otherwise they look exactly the same. And so in our studies, what we found were some very interesting phenomena, which is as the liquid evaporates and condenses in the channels, they form these sort of bridges. Sometimes they're single interface. And this is very similar to these interface configurations that we predicted could happen in microgravity. And so just passing, I'm showing you here how we're taking the work that we do in space and are applying it to fundamental research that we're doing on the ground at the nanoscale in order to help improve oil extraction from non-conventional sources. And it's been mentioned that I'm at MIT, so I think it's worthwhile for me to talk about some of the work I do at MIT. So at MIT, we're developing nanoporous atomically thin membranes based out of graphene. Graphene is single layer carbon. It's a crystalline structure that normally is impermeable to helium, the smallest molecule. And so what we do in the lab is we basically punch holes through the graphene, and we can control the size of the holes, their distribution, and so on. And so these are some examples of what holes in the support layer and what the graphene looks like on top. And just to go through real quickly, we grow the holes using oxygen plasma. So by exposing it to oxygen plasma for different times, we can make big holes for longer plasma time or smaller holes for smaller plasma time. And that enables us to create selective membranes that are able to filter, for example, dyes from ions or water from salt water, and so on. And we're showing that we can achieve very high permeabilities and selectivities with these cutting edge technologies. And so we're using these for water desalination, kidney replacement, so dialysis treatment, and also infusion reactors to help separate the fuels from the burnt reactors. Now, to get into the fast gear of the talk, so probably in the next 5 minutes, I'm going to go through tons of slides, but you'll probably see that in all of the research that I've talked to so far, people are needed to perform the experiments. And especially in space, some of the payloads that Dr. Das and I design, they're designed for people to operate them. And so we need people that are trained and able to operate payloads in space. And this leads into bioastronautics. We are developing a way to study how humans perform, behave, react to the space environment. We want to develop procedures that are safe, that reduce risk. And we want to have people trained that are not just astronauts, but are people like you, students, scientists, researchers that can be trained to then operate science and payloads in space. And so these next series of slides is going to talk you through some of the work I've been doing with the International Institute for Astronautical Sciences. And it's a course program that's available for anyone to sign up on. So if you're interested, just Google and find out. But I'll have the course names here, and I'll just talk you through real quickly what we do. So first off, the basic course is Fundamentals to Astronautics. We basically train people on what spaceflight looks like, the hardware, the aircraft, or the spacecraft, and how to fly the spacecraft. So we actually have space sims that people operate. And in the sims, we have actual spaceflight hardware that you operate. These are scientific instruments, and we train people how to use them. This is our mission control center, and we have different flight profiles for the spacecraft. And we're also showing here that we monitor people's biometrics, how stressed, their heart rate, blood pressure, all of that as they perform these sims. And then we gather all of this data, and we're able to produce publications talking about how to design the spaceflight so that it's less burdensome on the person, less physically burdensome, quicker to achieve, more versatile, and so on. And so related to mission planning, flight windows, and so on. When you're in a spacecraft, you need to be protected. And so you need to know how to operate and use an intravehicular activity spacesuit. So this is an actual spacesuit that's commercially developed by Fellow Frontier Design, a spacesuit development company. And so we get trained on how to operate, pressurize the spacesuit, emergency procedures. And part of the training is also feeling the forces. So when you're sitting in a simulator on the ground, you can't feel the G's and the microgravity. And so we go into aerobatic aircraft and we get trained on what those feel like. So these are different aircraft, and we often do training sometimes where we will fly the aircraft aerobatically in spacesuits. And I'm just showing here the G suit. So in high Gs, your blood will drain to your legs. And so you need to have countermeasures to prevent that. Here's one of our most recent classes that took part in January. And you'll probably notice one of the students has a very nice flag on her flight suit because that's where she's from. And so it's a very international program available from anyone to participate. Some of the other courses, retrain emergency procedures. So basically, if your spacecraft has to emergency land in water, how do you deal with that? How do you escape? How do you survive? So we do training at these facilities at Survival System USA in Groton, Connecticut. And then I have some comparison images with what NASA does to train their astronauts and what we do. We're constantly researching how to develop personal flotation devices and procedures. So NASA versus us. This is NASA, how they escape from the spacecraft. This is us. And you can see very high fidelity programs that we put together and formulate. Again, NASA versus us. NASA would be a few $1 million, and we're doing these for under $100,000. Very, very, very good program that we do. And then we also learn how to ingress a raft, very challenging to do in a spacesuit. And we monitor the biometrics as well. And on top of that, we're developing new technologies. Like I mentioned, we're designing new flotation devices. We're developing technologies to help with the defogging and also to help prevent water from getting into the suits. And one of the things that we do that no one else does is we train people in simulated parachute drops and what happens if your parachute lands on you in a spacesuit in water, how to survive. It's amazing, amazing programs. We have some of the best instructors. So this is that train astronauts. So Jose and Uliana. Uliana was one of the finalists for the NASA program. Jose is one of the astronaut instructors, and he teaches them about geology. So when astronauts go to the moon or Mars, this is what they'll be doing. They'll be mapping the moon, studying different rocks, and learning how to characterize features and interpolate and figure out the history of the surfaces that they observe. And we also get trained on the tools that the astronauts will likely be used. And this is one of the sites we were at. This is SP Crater in Arizona. And this is an example of some of the outcomes of the work that came out of our field trips. NASA will train their astronauts and develop some tools. And what we have done in the program is take these to the next level. So this is an example of a surface sampling tool with a window that allows people to study how the soils of the moon actually behave without exposing the soils to another environment. So that's what the sample looks like. You seal it, and then you can do a spectroscopy on it and get some results on the soil sample in a pristine environment. And I think this will be the last one on bioastronautics, is we also work with EVA suits, extravehicular activity spacesuits. These are the spacesuits that you wear outside the spacecraft. So in 2019, I worked very hard with the Canadian Space Agency to put together a research lab. And we built a gravity offset system that simulates the moon environment or the Martian environment. And you can sort of see, this is Shauna Pandya as she walks. It almost looks like she's walking on the moon. And so we have now this lab facility to study a whole lot of human factors related to surface moon projects that can be done on the moon, tools and so on. Great. So just going forward, in case time, I love this photo comparison between NASA and us. Okay, so the last topic is translating the work that you do, space science work in particular in my case, into businesses. And one of the first businesses that I launched was with Dr. Das, where we co-founded TMS Robotics and Academics. This was a program that we built after finding both Dr. Das and I had taught at the University of Toronto. Dr. Das also taught at Ryerson University and obviously now a professor at UMES. What we found is that there is a big gap between high school and first year undergrad. And it's not the student's fault that there's a gap. It's the way that the education system exists. But there is a need to bridge that gap in the experiences that students have. You go from high school where you're used to the teacher taking attendance, hand-holding you, giving you homework and checking that you did your homework, to being an undergrad where no one takes attendance, no one checks your homework, and it's up to you to be disciplined. And so we wanted to bridge that gap, and that was the motivation for TMS Robotics and Academics. And what we did was we basically took the university level curriculum and broke it down into bite-sized modules that we then taught to elementary and high school students. And we used robotics as sort of the first topic in which to do that. The second business was looking at, if people are going to be working in space, they need to be fed. And I love food, and I want to have good food in space. And this motivated a new business called Astrius, Ignition Space Food, to develop new foods for spaceflight. So for TMS, Robotics and Academics, what we did was take that university curriculum and teach it to elementary school students. And I have some key points here. One, we had students as young as 6-year-old take part in our program, and we taught them how to build like a Segway style robot. If you don't know what that means, it's a robot that balances itself on 2 wheels and can move forward or backwards, and it balances itself. And we had 6-year-olds build this, and they built it. One of the challenges we faced was convincing parents to let their kids join the program because the parents thought that this would be way above their heads. We told them, no, send us your kids, we will teach them. And so we taught these kids calculus. We taught them how to implement PID control loops, sensor design, calibration, programming, and autonomy. They did it all themselves. Sometimes the parents would come and make sure that the kids were doing it themselves and that we weren't doing it for the kids and saying that they were doing it. And the kids loved it, the parents loved it, and the business just grew by word of mouth. And eventually we found ourselves with the Toronto District School Board to Toronto Catholic School Board and with the Ontario Schools Education Board. And we ran hundreds of students through our workshops. So what we learned from that was definitely business planning, how to hire, how to fund, how to do sales. But this is showing like there is a need, and we were able to take our knowledge that we learned from the lab and how we learned to do research and apply it to teach and build a stronger community starting from very young students. And then for the second business, we spoke with astronauts about, what were your top 5 issues in space? And many of them talk about the food. So the food in space is dehydrated to save on the launch cost. And then when the astronaut wants to eat the food, they take the pouch, put it in this machine that only injects hot water. And then the astronauts mush the food around, cut it open and eat it. And so all the food that they eat is usually mushy, gooey. Sometimes they make pizza, but it's also gooey. It uses all this sauce and soft pita bread for the meals. And so the astronauts said that they miss crunch in space. Also, astronauts have to take supplements, multivitamins, to keep their health up because there's no sunlight and so on in this tin can of a spacecraft. But they often didn't take their pills because they didn't like it. And so what we did in Astrius was we designed a meal, or not a meal, but a multi-supplement that provided the astronauts with all the nutrients that they need, plus was crunchy, so we had different textural contrasts, plus was loaded with nootropics that would improve their mental health, cognitive health. And we had some fun elements in there like pop rocks. And so this is a product that we're currently selling, not just to astronauts, but also to the general public. It's available for purchase, and we have other products down the line. Some of the other projects that we're working on is how to cook foods. So NASA and other space agencies are focused on how to grow foods in space. Hardly anyone is looking at how do you cook the food that you grow. And so that is what our company is developing. And just so you know, about $2 million in food is wasted. This is food that has been flown to space. It's just thrown out because no one wants to eat it. $2 million roughly every 6 months. That's terrible. And so this is what we're hoping to do. And we're learning a lot along the way. So finally, to wrap up the talk, and I apologize for going a bit over here, scientists, researchers, and everyone, I think, is searching for the logos. The reason people do science is to find the logos. The scientific method is one tool that we'll use, but in order for it to work, we have to remain objective, and we have to be willing to challenge current theories if experiments are showing that they must be challenged. And this obviously can lead to friction between people, research groups, and Dr. Das and I are very familiar with what that can mean when we try to present our discoveries. But hey, it leads to new discoveries, and that's a big advantage. And as Dr. Das had talked about earlier, theory should be validated by experiments. People can do just theory or just experiments, but doing both is better than just doing one. So keep that in mind as you plan your careers. And use the resources that you have. You have a great opportunity here with education, with the people that are in your network. Make use of your resources to make the world a better place. And keep in mind that there is a world out there. So get out there, meet different people from different places with different experiences, and it'll help you come up with new ideas, new research questions, and feedback to bettering our world. And so with that, I'll come back to the brain teaser. Hopefully you had some time to think about how it's going to behave. So I'll show you the flight. This was done by a colleague of mine, a PhD student in Toronto. So we're exposing it to the microgravity environment. And there it is. That's the configuration right there, the stable configuration. And I took a photo. It's here, and I zoomed up photo. So if you guessed this is how the liquid would behave, congratulations. And so with that, I bring my talk to an end. Thank you very much for your attention, and I can open it up to well, I'll pass it back to the chair of this session to move forward.
Okay. Thank you, Dr. Persad, for such a very enlightening deliberation. The lecture basically started from very fundamental issues like how the things are developed, very simple theory of thermodynamics and classical physics, and then using that, that has been applied to various physics of fluids and how that fluids behaves in space and several aspects of space science, especially mostly the fluidic states when they are in this zero gravity or say very low gravity conditions. And finally, the last two things, that means the foods in space and the life in space, that's really very interesting. So we hope our audience students have really enjoyed this lecture. There are a few questions. I'll just sharing the questions over here. That will be very useful. Let me share just the screen. Yeah. So here are a few questions. Yeah. Okay. So the first one is different points on Earth have different gravities. While launching a satellite, we do so keeping in mind the Earth's center of mass. But different points like mountains and so on will have different gravities. I mean, he's talking about the change in the gravitational constants. Yeah, change in the acceleration due to gravity. So wouldn't the satellite shift from its original orbit while it's traveling through every positions of Earth?
Okay, great question. So the answer is yes. Definitely the center of mass of the Earth is taken into account. So that's true. The changes as you have different launch sites, so how the local gravitational field is different, yes, that's also taken into account. But when it comes for a launch, the dominant force is going to be the rocket propulsion versus the small changes in the that you could experience day to day from changes in the gravitational field at that local point. So to give you an idea, the local changes that we're talking about globally, worldwide, probably on the order of 50 milli-Gs, so 10 to the minus 3 Gs, very, very small. Whereas in a rocket, you're dealing with thousands and thousands of thrust newtons. So they will certainly overcome any of those changes. So where this becomes really important is once the spacecraft is in orbit around the Earth, that is where these changes in gravitational fields, and especially as it's orbiting different parts of the Earth, plus you have the moon phases, the moon cycles that also impact where that spacecraft is going to be. Plus you have the time of the year, so the distance of the Earth from the sun, as that's also going to impact the gravitational field experienced by the spacecraft. So most spacecraft will have propulsion systems in them in order to basically boost the orbit. So if the spacecraft is found to be changing, or let's say it's crashing, tends to crash towards the Earth, they'll boost the orbit a little bit. Just fire the thrusters a little bit, boost the orbit, and that'll keep the spacecraft going for a few more months. So if a spacecraft does not have a way to actively change or fine-tune the orbit, then it's going to have it's eventually going to deviate from that orbit. Even if the gravity field was uniform, there's micrometeorites around the Earth in that low Earth orbit atmosphere. There's still an atmosphere up there, and it's always going to slow down the spacecraft. The space station experiences that, and every couple days or couple weeks it has to boost its orbit. So the answer is yes, it's affected, but most spacecraft will have boosters built in, and they can make slight adjustments. PC. Oh, sorry, go ahead.
No, okay. Piyush, are you there, Piyush?
Yeah, I'm just back. Actually, I faced some network issues.
So, yeah.
As I can see the chat, I'm happy to very quickly answer the questions that are in there. Oh, okay.
Okay. So why does a liquid vapor temperature jump occurs at the interface, while the temperature should remain constant when liquid evaporates by taking some latent heat?
Yes. So when you talk about the latent heat, that is an equilibrium property of the liquid. So the way that the latent heat is measured is you basically have water. Let's say you have water, and to measure it accurately, you have pure water. That's going to change into its pure vapor in a closed container, not into the open atmosphere, to a closed container, and you're providing a heat source into the water to then get it to evaporate. The condition where the water changes into a vapor, that's all going to happen on the phase change line, that saturation curve line, and that's going to be an equilibrium condition. And you're not going to have a temperature jump across that system because it's going to be in equilibrium. So think of it as the latent heat is like this very specific condition of an equilibrium system. What I talk about in evaporation is what happens after after the liquid has enough energy to evaporate. It's no longer an equilibrium system at that point. It's non-equilibrium because now the liquid is evaporating. So latent heat, equilibrium property, evaporation, non-equilibrium. Latent heat, you're not going to have a temperature jump. In evaporation, you will. So hopefully that helps answer the question there.
Okay.
Aaron, your talk is really was outstanding. So I have a silly question that what will be the form of a water drop? That is, water drop is spherical in microgravity atmosphere. That is, you take 10 to the power minus 7 into G.
Yes. Okay. Great question. So in the work that I presented in this talk, I focused entirely on liquids that were in sealed containers.
Okay.
So what would happen if you had the liquid and it's not in a sealed container? Well, one, the pressure is no longer confined. The energy, well, the mass will likely no longer be confined because now you can have interaction with gas molecules and the liquid that are not water. So for example, oxygen, nitrogen can dissolve into the water. If it's in sort of an ideal, let's say, open environment where there's no wind draft, nothing like that, what you would expect to happen is the water will minimize its surface area for a given volume. So it will take on a purely spherical shape in that case. So the water that you see when astronauts, have a blob of water floating in the space station, it's never purely spherical. And the reason for that is because of all of these other compounding factors and external forces, wind drag, temperature gradients, all of these different things impact the different shape of the water. But if you were able to have an isothermal environment, just pure water with water vapor, and the water isn't in contact with a container, it's just freely allowed to grow or shrink or do whatever it needs to do, it will be a spherical shape.
Okay. Thank you.
Okay. So another question is from Dr. Gautam Manna. So when we measure the gravity, is the equivalence principle satisfied? That is about the inertial mass is equivalent with the gravitational mass.
Yeah, it's a good question. So let me say, first of all, that mass is mass. Mass is mass, but if you're approaching these very strange relativistic environments where your mass is accelerating to near the speed of light, things like that, then yes, this question, very good question, and there is tons of research being done into this. I don't have any experience in this field, so I can't say what they have found. But what I can say is this: if the principle were not satisfied, there would be publications coming out left, right, and center about it. So I think right now, Einstein's law, basically if you have a mass and it's moving very quickly and you are somehow able to measure that mass, versus if you have a mass and it's just exposed to a gravitational field and you measure the mass, there's no break in the science there. There's no break in the findings, in the empirical data there, as far as I am aware. There are some tricks that can be done to create what's called negative mass, but like I say, those are tricks, and for all practicality, it's not something that you would encounter in any meaningful way in your day-to-day experience. So I believe the answer, as far as I can tell, is yes, they're going to be equivalent, with the caveat that, in my experience, I'm not in the relativistic world. I don't work in the relativistic world. Yeah. Great question, though.
I'll quickly take two short questions from our students. The first one is, can a star be turned into a planet?
Yeah, good question. The answer is no one knows, because no one has observed it. But the theories is showing that has to be the case, because one of the questions earlier was, how did the universe form? So one of the big theories that is currently now under challenge is the Big Bang theory, and I love talking about that. But basically, everything came from nothing. Just think about that for 2 seconds. You can tell there's something wrong with that statement already. But Big Bang, then first molecules, then the stars, and the stars are the factories that produce the higher elements that then produce the planets. So in short, yes, a star can turn into a planet, yes, but no one has seen it happen.
Okay, thank you. And I'll take a final questions. Does electric or magnetic field have any effect on gravity?
So this depends, again, on how you want to describe gravity. Earlier, I talked about gravity as a force, as an acceleration. So in terms of an acceleration, the answer is no. I don't think anyone has found a way to use magnetic or electric fields to change the gravitational field. But if you talk about gravity in terms of a force, then yes, if you have, for example, a magnet and it has a mass, and you expose it to another magnet above it, that magnetic field is going to pull that other magnet against the gravitational field. It's not because it's changing the gravitational field, it's just because of the force balance between the force of the weight, essentially, versus the magnetic force. So If you talk about fields, the answer is no. But if you talk about forces, the answer is yes.
And I have small questions that
Yes.
I have already seen in various websites that there are several agencies. They're basically selling lands and plots in moons. What are the legal status of these things, or it's a future like this?
That is such a great question. Now we get into space policy, and space policy or space law is one of the most important fields of space research because it's going to dictate what people are allowed and not allowed to do in space. So when it comes to land, I think the United Nations, it's called the UN COSPOS, the United Nations Committee on the Peaceful Use of Outer Space. They put together some regulations for from UN. How to enforce that is a different story, but basically the regulations say that no one can own property on the moon. So you can't own property. You can't say this is US property, but you can lay claim to a property. So what that means is if you land there and you're mining the resources there, then you sort of have a claim there. Like no one else can come and push you out to then mine there because you were there first. So it's sort of a nuance. It's like, okay, what's the difference? The difference is you're not owning the property, it's you're using it. And now, do you own what you extract? That's a whole different story. But as far as I can tell, I don't think people can own, but that's UN. Other countries may have different policies. Other countries have the policy that if they land there, they develop there, they build habitats, they build, solar panels, and their astronauts will live in there. They invested all this resource to make that happen, so they should own what they invested in. And it's hard to argue against that as well. But that would be a non-UN view. And then to go a little bit further, it's let's say you have property on space and someone attacks it. How do you defend that? So you now need a space force to help with that. And so you get into military, and can space be used for military, or the moon, can it be used as a site to do military research? Whole policies and treaties on that. So the short answer is, as far as I'm aware on the UN policies, the answer is no. But again, policies change with lobbying, and I don't know if that has changed. I want to have McDonald's on the moon, so I hope that happens.
Okay, so Kaushik, please.
Yeah, so Aaron, I have one question for you. So I regularly get these, read these articles about this asteroid mining. Apparently, asteroids are full of minerals and valuable metals and diamonds, stuff like that. So there are various companies. There are so many companies now. They are creating a business based on the fact that they will go and catch those asteroids and they will mine from those asteroids. So how futuristic is that, and where we are in that mechanism? I mean, at this moment it sounds like a real sci-fi project, but people are putting money in there, and these companies are becoming big. So how far we are from that reality of asteroid mining? And like as Elon Musk says, and Jeff Bezos of Amazon says, that they are creating new habitats. They're planning to create new habitats in other planets apart from the Earth. So where are we in that pursuit?
Yeah, great questions, Kaushik. So the first question about mining, if I were to reduce it or distill it, mining is taking something from under the ground and bringing it up at a high level. So yes, there are companies, many companies that are competing for rights to some of the astronauts some of the asteroids that have been identified to hold, for example, very precious metals, like even more precious than gold. There's one asteroid that's thought to be entirely, this is maybe me being exaggerating a bit, but entirely diamond. And so there's companies that want to mine that. Other asteroids are thought to be primarily gold, and so companies want to mine that. And so there's a lot of lobbying with these policymakers to make it possible for them to go mine and own what they mine. The ripple effects is very challenging to quantify. So one of the reasons why gold is so valuable is because it's rare and it's difficult to get, difficult to mine. If you now have a company that has found basically a mountain size of pure gold and they bring it to Earth, now gold is no longer a rare resource. And so what will happen to the price of gold? And so these are the economics and analysis that has to be done there as well. But the short answer is yes, there are real companies that are developing real technologies to mine. Has mining on an asteroid already happened? Well, based on my definition of mining is getting in there, pulling something out, the short answer is yes. There have been satellites that have been launched to asteroids, have landed, drilled, gathered samples, and came back and brought those samples back. So space mining has happened, but is it romantic? You know, have they brought back a diamond ring? No, it's just a soil sample, you know, something like that. So yes. Now, I think there's a big future for mining. If you look at the class of astronauts that were selected by the US this year, one of the astronauts, Denise, who was in our IIAS program in the first class, she was selected as an astronaut, and her background is drilling, oil refinery drilling, which is very, very close to mining and getting resources up to the surface. And so I think that says a lot about a government space program putting an emphasis on mining. Your second question related to habitats. I have heard very different viewpoints on whether or not we should have habitats on the moon or Mars. I think it's a given that if there's going to be a human mission on Moon or Mars, they need a habitat to survive there. The question is what that habitat should look like. If you Google, you know, Martian habitat, you will probably see images of these bulbs or glass domes that are scattered around the surface with solar panels, and everyone's living on the surface. But in reality, there's tons of radiation on Mars, tons of radiation. And what is needed to protect people from that radiation is more than glass. It's massive amounts of material. And the reality of being able to send that material from Earth to Mars just kills any mission because of the cost. And so in reality, it would be best to make use of resources that are already on Mars, and that could mean digging underground. And so maybe habitats would likely be underground or cavern to help protect against radiation. Or the other alternative would be to 3D print. So use the materials that are there, you grind them, you have a binder, and now you can 3D print your habitat out of this very robust material that can help provide some insulation from radiation. On the moon, I don't know the numbers for radiation levels on Mars versus Moon versus Earth, but from what I've heard, for Mars, it's unlikely that you'll have a surface habitat. But for Moon, it's the same thing. I think if you look at Moon habitats, you're more likely to see images come up of habitats that are covered with lunar regolith. And the whole idea there is to, again, use the regolith to protect against the radiation. Jeff Bezos, Elon Musk, definitely two people, but there are many others that are also working on habitat designs. And what I love about them is they don't worry about radiation. They don't worry about the cost. They have a vision, and they have the freedom to dream. There's nothing wrong with designing your habitat, making a 3D diagram, sharing it with the world, There's nothing wrong with that, and I think it's very needed for people to be willing to dream like that. Whether or not the habitat's going to look like what they think it's going to look like is a different story, but I think they're doing people, or say humanity in general, I think they're doing humanity a good service in bringing these ideas to the forefront, because I would never dream about—
That's an excellent point.
Yeah.
Because see, you had to dream before you do something, right? Somebody had to dream about electric cars, just like Elon Musk did, and then it came into a reality. So that the power of dreaming is so important, that you do something which is not there yet, which is not here yet, and that should be the motivation of every science and technology students also, isn't it?
Yes, I agree. And that's one of the reasons why I said in my concluding slide to get out there and discover the world, discover other people from other cultures, male, female, not just guys with guys, but different perspectives as well. When I say different cultures, I don't just mean, stay within India, but understand how Eastern versus Western thinking happens. And when I say diversity of experiences, I mean also like ages. Like I learn so much from when I teach the students and the high school students and the undergrads. I learn so much from them because they have a unique perspective and experience. I also learned so much from my mentors like Dr. Das and my supervisors and so on, because they have experience, and that brings a new set of perspectives. And so, surround yourself with both younger people but also older people, and that is the catalyst from which these dreams, I think, will come.
Excuse me, sir. Sir.
Yes, Sinjin, please.
So actually, you mistakenly skipped my question. So my question was, what happens when a spacecraft runs out of fuel while it's in space?
Yeah. So the short answer is, hopefully it quickly deorbits. So right now there is a law in place, again for space policy, that every satellite, every spacecraft that launches has to have a reservoir of fuel. And the reservoir of fuel is in order to deorbit the spacecraft and have it crash or burn up in the atmosphere at its end of life. In the past, what would happen is you would have spacecraft that would go up there, orbit the Earth, do their research, be decommissioned, and now it's just junk orbiting the Earth. And based on the orbit and it might take hundreds, thousands of years before it eventually deorbits and crashes into the Earth. And so space junk is a big, big problem. And so one of the ways to combat space junk is now every satellite that launches has to have a deorbit strategy. Most satellites will choose to use a thruster. So the thruster is not only used to correct the orbit and keep it in orbit, but at the end of life, it just basically rams it into the Earth's atmosphere and burns it up. So if a spacecraft did run out of fuel, it really depends on its orbit. If the orbit is basically towards the Earth, it'll burn up and that's it. However, if the orbit is a bit more stable, it'll just stay up there for who knows how long, 20 years, 100 years, I don't know. Yeah.
Okay, so I think there is no more questions. And if you have any questions, you can also email us so that we can communicate with Aaron and we'll make you acquainted with these answers. So, Dr. Aaron, very, very thank to you for giving such a long time and these valuable discussions with our students and with the audience, and with the various aspects of this fundamental physics to apply in space. And actually, we also learned various things in space research also. So on behalf of the Department of Physics and on behalf of our Prabhat Kumar College Contai and our associate partner, the Physics PK College Contai Physics Alumni Association, we sincerely thank you again for you, and hopefully we'll maybe we have some time, we'll arrange for a direct face-to-face lectures in our college also, and maybe at later stage. So thank you once again. And now I'd like to take the privilege to thank Dr. Kaushik Shankar Das for making us giving us help in various ways in communicating with Aarons and arranging all these things. We express our thanks to Dr. Ratan Sarkar, Assistant Professor of Teachers Training Department, PK College Contai, and Mr. Bivas Mojumdar, Assistant Professor of Mathematics, for surely controlling all the technical support with this Google Meet platform and the YouTube live streaming. Thank you so much. And it's we must thank our alma mater, the Alumni Association, PK College PK College Contai Physics Alumni Consortium, for their proposal for making such a memorial lectures, and finally it has come to success. We express our, on behalf of the organizer, we express our sincere thanks to our Honorable Principal Sir and also the governing body of PK College Contai for their necessary permissions and associated helps in arranging this program. And also we are thankful to our colleagues of our department as well as the college for their support in various direct and indirect ways and encouraging us to organizing such events. And finally, we are thankful to all the participants, especially our students, for whom we are arranging this lecture, so that they get benefited, they get recharged, and I hope this lecture will motivate them to take physics, not only to just study physics, but to take the research as a passion for their future scope. So with this, I will thank all the stakeholders from all the corners who are associated with this program, and special thanks to again Dr. Aaron and Dr. Das for their valuable time with us. So thank you all. Thank you very much.
Great. Thank you so much for this opportunity, and I'm more than happy to come back at a future time, in person or virtually. Thank you so much.
Thank you.
Thank you. Thank you.
Thank you.
Okay, bye for now.
Okay, sure. Bye-bye. And we are concluding this event today. So thank you all.
Well, Prajita, so I'm ending the session. Hello?
Hello.
হ্যাঁ, so আমি end করে দিচ্ছি তাহলে.
হ্যাঁ.
Okay, thank you.
Okay.